isomerism. So now, if we study the structural formula of butane, remember butane has but, so 4 carbon atoms, or other higher hydrocarbons. So what does that tell us? That from butane should be the least for you to talk. When you're talking about isomerism, 4 carbon atoms should be the least you're considering. So if we study the structural formula of butane or other higher hydrocarbons of the alkane series, we will observe that it is possible to arrange the atoms in the molecules in more than one way. Now this means that it is possible to have more than one different structural arrangement for the same molecular formula. That's so almost similar to what we're talking about allotropy. Now isomerism is the existence of 2 or more compounds with the same molecular formula but different molecular structures. So existence of 2 or more compounds, and these compounds are called isomers. Just like in allotropy, the different forms were called allotropes. Now in isomerism, the different compounds of the same molecular structure they're called isomers. So if we want to use that mesomer again, mesomy will be an isomer of mesomer, you understand? So isomerism is the existence of 2 or more compounds known as isomers with the same molecular formula but different molecular structures. Now therefore, isomers are molecules with the same molecular formula, that is, the same number of atoms of each element, but different structural or spatial arrangements. Spatial. That spatial means in space, the arrangement in space. So, but different spatial arrangements of the atoms within the molecule. Now, you have to take note that isomers can be split into 2 broad groups, which we want to discuss now. Isomers can be split into 2 broad groups. The first one being structural isomers and then stereoisomers. From the word structural isomers, it's going to be dealing with how they are arranged, how their structures are arranged in space, spatial arrangements. And then stereoisomers is not stereo F88.1 FM. Stereoisomers is just optical isomers. You will see when we get there, but let's look at them one by one. Now, we get to structural isomers. Now, we can further divide structural isomers into 3, which will be number 1, chain isomers, number 2, position isomers, and then number 3, functional isomers. So let's look at them one by one. Chain isomers. What are chain isomers? Chain isomers are molecules with the same molecular formula but different arrangement of the carbon skeleton. Remember, when we say molecular formula, we're talking about CnH2n plus 2 for alkanes, CnH2n plus for alkenes, CnH2n minus 1 for alkyne, like that. So they have the same molecular formula but different arrangement of the carbon skeleton. That's probably what we have been doing when we have been doing naming of alkane, alkyne, and all those ones, the structures we've been drawing. So look at this. Here, carbon atoms can be arranged either as one continuous chain, remember when we'll be counting the parent chain, or a chain with multiple side groups. We'll be seeing the functional groups linked to one carbon and so on. So like that. Multiple side groups of carbon branching off, so it can either be a long straight chain or branches. These carbon atoms can be branched in more than one way as the number of carbon increases. So we're going to see an example. Remember we said butane. Now look at the diagram. Butane has CH3 at this end, CH3 at the other end, and then CH2 2 times in between. That's why I wrote that formula, CH2 2 times, then CH3 at the other end. If you look at that structure and compare it with the one beneath, you would understand. Now let me explain what they were. That the one I drew and put chains, and you see H linked to C, and that one is called structural formula. Then the one I wrote, CH3, then open a bracket, CH2 into 2, and CH3 is called condensed formula. So let's be technical now and professional. So when I say draw a structural formula, you are going to draw it with branches like this H is showing, you show the bond, you show the link. That's structural formula. But if I say write the condensed formula, you're going to write this. It's almost a structure, but you're not going to put the dashes and how those ones. So this is condensed. The structure has chain, and the condensed is just written in brackets used to tell how many of this one is intermediate. Okay. Now, if you look at that butane, the one by your left is N-butane, normal butane. The N-butane means normal butane, but I did not write N-butane, but it has normal butane. There is no branch. It's just butane. Now, if you look at your right, you see that if you count the number of carbon and number of hydrogen, they are still the same as this one we did by your left, the butane. So, but what happened is that at the middle, instead of having CH2 two times, we have only one C at the middle. Then the other C is branched on that C at the middle. So we still have the same number of C, but then we have a group branched at a carbon atom, just like we explained when we're reading that. Now, when you do that, the name changes. But remember, this is still an isomer of butane, because it is the existence of another compound with the same molecular formula. It's still C4H10, but different molecular structures. They are now looking different in the structure. That's just what it is. Now, if you look at the way we named alkanes the other time, you'll see when we start, even if you want to start the numbering from this left hand side, the middle will still be 2. Want to start from this side, the middle will still be 2, so you can start anywhere. I started from the other side. So 1, 2. So it means and you know that CH3 is methyl group, remember. So methyl group is branched on the second carbon. So you write 2 methyl, and you now count the straight chain. Straight chain is how many? 1, 2, 3. That 3 means it's prop. Okay, so, and it's an alkane, so it's propane. Alright, so the name of the compound is now 2-methylpropane. Now, 2-methylpropane is an isomer of butane. Why? Because it still has the same the same molecular formula, C4H10, as butane. It's just that it differs. It now looks different in structure, and that's what we call isomerism. So, 2-methylpropane is an isomer of butane. So that's why I wrote there isobutane. Isobutane means isomer of butane. You can see isopropane. No, isopropane cannot happen because we said the least should be butane. It should be 4 carbon atoms. So you can have isohexane, like that. And if whenever you see iso whatever, it means isomer of. You understand? All right. So 2-methylpropane is an isomer of butane. Now that's the first type of structural isomerism. Let's look at the second type, position isomers. Position isomers are based on the movement of a functional group in the molecule. Now, in this case, nothing else about the molecule changes, except that the functional group changes position. So if the functional group was on the first carbon, you can change the functional group to the second carbon or the third carbon, as the case may be. Now, the name will be altered slightly to indicate where the functional group is located in the molecule. So as you change it, the name is altered. Remember, this one was 2-methyl. If the functional group was methyl like this, and you change it to the third carbon, it becomes 3-methyl, you understand? So the name will be altered like that, just to indicate where the position is jumping to, where the new position is. So let's look at that example down there. Now, we have 1 bromopropane, and then the other one we have 2 bromopropane. What happened? In 1 bromopropane, the bromine functional group was attached to the first carbon on our parent chain. But see, on the other one, I shifted the bromine to the second carbon, and the name changed to 2 bromopropane. So you understand, that's position isomerism. So 1 bromopropane and 2 bromopropane are position isomers of what? Propane. All right. Now, take note, don't be confused. You see, I drew the structure of 1 bromopropane and still wrote the condensed formula. Remember what we said condensed formula is? The condensed formula CH3, CH2, CH2Br. It's the same thing as that structure, but now in condensed form. Same thing with 2 bromopropane. By the right, you see a condensed formula of that structure. Now, take note of this. Number 1, chain isomerism and position isomerism can be mixed to form more isomers. You can mix chain isomerism and position isomerism, and both of them happen in the same isomer just to form more isomers. Now look at this. Butanol, yes, 4 carbon atoms linked with alcohol functional group, alkanols. So butanol has 2 isomers when considering it as a position isomer. That's 4 carbon chain. Now look at it. Butan 1-ol and butan 2-ol. What happened? In butan 1-ol, you see, I'm using condensed formula in this. I'm not using the structural formula now. I'm using condensed formula. It's almost the same thing. Just using this so that you understand better condensed formula, how it differs from structural formula. You see, in the butan 1-ol, the OH is linked to the first carbon, right? So that's what butan. How many? The first carbon, 1, and then the functional group. Remember, when you want to write attach the functional group, alkanol functional group, you write all. Remember, you said if it's in as prefix, you say hydroxy, but if it's as suffix, you say all. Remember those things. Don't forget those things easily. So in butan 1-ol, the OH group, the hydroxyl group, is attached to the first carbon. So the name has to become butan 1 because first carbon 1-ol. Now, but on the second one now, butan 2-ol, the OH, the hydroxyl group, is attached, hydroxyl or alcohol group, so it's the same thing. It's attached to the second carbon, so it changes to butan 2-ol. You see how we used position isomers there. Now, listen. But when mixed with chain isomerism, 2 more isomers can be created. Look at this. 2-methylpropan 1-ol. Have you seen that? Good. So, instead of, you see, the first one, OH, was linked to this first straight chain. But now we can even alter the straight chain also and form some branches. Like, since it's 4 carbon atoms, we can only form 1 branch since 4 is the least. So with the butane, I've now formed a CH3 group. If you count everything apart from the OH in butan 1-ol, it was C4H3 plus 2 plus 2 7 8 9 H9 apart from the OH. If you count the one in 2-methylpropan 1-ol, it's still C4 and H9. You see that? So nothing changed, but I changed the structure. I changed the structure. I changed the arrangement, spatial arrangement of this one. So I'm mixing chain isomerism with position isomerism. Remember, position was just changing position of the functional group. But now use this chain isomer and change it to branch. So, and mixed it with the position. So we now have 2-methylpropan 1-ol. And if I change the other one that was butan 2-ol, it becomes 2-methylpropan 2-ol. Study that properly and you'll see that we mixed position chain isomer with position isomer to form a more isomers. That's one thing you should note. For the second thing is, you can also get position isomers on benzene rings. Remember we did aromatic compounds that they have benzene rings as their major unit. Now consider the molecular formula C7H7Cl. There are 4 different isomers possible depending on the position of the chlorine atom. Now that means, since we are talking of position, we can be changing where the chlorine atom is consistently, change until we have something different. Now, in one case, it can be attached to the side group carbon atom, and then there are 3 other possible positions it could have around the ring. Now, we said in one case, that's first of all the first case is that it can be attached to the side group carbon atom. So look at the 4 benzene structures I drew there. The first one was standing alone, isn't it? The first one is CH2Cl on the first carbon. I'm saying that's the first carbon now. You see that CH2 is standing next to Cl. Cl is joined with that side group, so it's just attached to the side group. But now we can still alternate, change position. Now we said there are 3 other possible positions it could be around the ring. That is next to the CH3 group. So if we change that, remember in your in your, okay, if we change that Cl and bring it to the next thing, we are going to the right now. You see the second diagram. Cl now comes to this. We are changing position of the chlorine chloro functional group. Change it to this way. Now next, but one, not but one. Not but one now, I'm not talking about butanol now. Next, but one to the CH3 group. We are saying but one as you skip one. Next, but skip one. Next, but one, you skip one. You know, you have already tested that. You've already done that in the other part. You've shifted it to that point. Shift it to the next point. So that's next, but one to the CH3 group. It has been shifted to this point. Now, you can also shift it, you know, it's this change position to be opposite the CH3 group. Take note, you correct that first diagram. I wrote CH2Cl. You change it to CH3Cl. Yeah, thank you. So you see that you cannot change it back. You cannot keep continuing going anti-clockwise or clockwise now. You cannot keep continuing. If you take it back to this point, it's not the same thing as counting. If you count anti-clockwise, it will still end up being the same thing as when it was the other way. So opposite is the same thing. Just be very technical while listening to this so that you understand better. All right, so that's chain isomers. That's position isomers. We've discussed chain isomers. I will discuss position isomers, and now we can mix chain and position isomers together to form more isomers. Now let's look at the third type of structural isomerism, which is functional isomers. Now these are isomers where the molecular formula remains the same but contain more than one functional groups. The molecular formula, remember when I said molecular formula, we should be thinking of the CnH2n plus 2 or CnH2n if it's alkene and the rest. So it remains the same but contain more than one functional group. Example, CH3 or C3H6O could be either propanol. Propanol is an aldehyde, or it could be a propanone, which is a ketone. Propanol, an alcohol, is an aldehyde, aldehyde. But propanone is a ketone. So you see now, it's having more than one functional group, but it's the same molecular formula, C3H6O. Now let's look at how that happened. Look at the difference between this propanol structure and the propanone. The propanol structure has C linked with O and H as a functional group, but the propanone is C linked with O alone, then the methyl group and the two methyl group linked with the carbon here. But in general, they all have 3 carbon atoms, 6 hydrogen atoms, and 1 oxygen, but they are different functional groups now. So when that happens, that's example of functional isomer. That's the first case. Number 2, C3H6O2, that's just one O added to number 1 we're discussing, can be propanoic acid. Propanoic acid is a carboxylic acid. When you get to SO3, you understand all this perfectly. Or it can be methyl ethanoate. Methyl ethanoate is an ester, among others. Can be even more than these two we are mentioning. So you see that 2 functional groups are mentioned, but the same molecular formula. Now, see the difference between propanoic acid and methyl ethanoate. Propanoic acid has C. Now I'm looking at the functional group now, the ending now. That end has C linked to O and the other one linked to OH. But in methyl ethanoate, the C is linked to O and linked to OCH3. That's the difference. So that's the 2 functional groups. But if you look at them carefully, they all have 3 carbon atoms. They both have 3 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. So we have seen now that molecular formula can remain the same, but the carbon, but they contain more than 1 functional groups. So you see that classwork there. We should have been doing it in class. We'll still do it when we resume, but if you follow, you will see properly what I did there. It's a draw a structural isomers of the following: 1, 2-methylpentane and 3-methylpentane. If you see when we did number 1 chain isomers, you see we did 2-methylpropane. You can follow the same way and do 2-methylpentane and 3-methylpentane. And the second one, 1 butene and 2 butene. I did that one for you. 1 butene has the double bond. You know, double bond is the reason why it's called in. Butene means 4 carbon atoms, but it's an alkene. Now that alkene is on the first carbon for you to call it 1-butene. Now it will be on the second carbon. The double bond should be on the second carbon for you to call it 2-butene. So that's what you see there. Study it very well. You don't have that time to be saying I don't understand. Study it. When we resume, we'll still do it, but you must know it. Now there's an assignment for you there about that. I just wrote it there so that I will not forget. So make sure you do it. You will draw all the 5 isomers of hexane. It's very simple. And then all the 9 isomers of heptane. By the time you draw the normal chain, you can now start disintegrating, changing position or branching them until you have a better. All right. Now we said we have we can divide you can split isomers into 2 broad groups, and we have discussed structural isomers. Now let's discuss stereoisomers. That's stereoisomerism. There are 2 main types of stereoisomerism. We have geometric isomerism, and then we have optical isomerism. Now, what's geometric isomerism? Now, there is a free rotation about the carbon-carbon single bonds. Whenever you have single bond, it can rotate. Now, I want you to picture this. Just think, imagine this. That you carry one small orange. You know these oranges that have not matured yet on the tree. Just pluck 2 of them, small ones. We used to use it. We used it when we were little to play, fix it up, and then construct some things, and then it forms a house. It forms something, just structures. They use it a lot in chemistry lab to show things to children. Now, cut 2 of them. If you cut 2 of them, the small ones. Now, you will carry one strong stick, a stick that will not break easily. It can be broomstick if you wish. But now, fix one at the center of one orange, fix the other point at the center of the other orange. You just created, you can hold the broom at the center, not the long broom, very short broom that you can just hold at the center, and then the 2 oranges will lift and follow you in that structure. Now, what you are doing is you've created a single bond. That's how a single bond is. Now, what you will do now is hold one orange, or just hold the broomstick. If you hold the broomstick, try to rotate one orange. You see, it will rotate, isn't it? It will rotate. It will turn freely. It will turn freely. And if you hold it, turn the other one, it will turn freely. But now, carry another orange, 2 more oranges. You've kept this one aside, this one that there's a single bond. Fixing the other one in such a way that you now have 2 brooms. 2 brooms, like a double bond now. Now, hold the 2 brooms at the center and try to rotate the one orange. This time it will not rotate. It will not rotate. And there is a reason. Now, if you see that, you will discover that in double bonds, the bond is stronger, it's rigid, it cannot rotate. But in single bonds, the different axes, they can rotate. So that's why I'm saying there's a free rotation about the carbon-carbon. The 2 carbon now is the 2 oranges. A carbon-carbon single bond. Single bond is a broom at the middle. In alkanes, so all saturated hydrocarbons that have, saturated hydrocarbons have single bonds. All single bonds can rotate. There's a free rotation. That is in this example of the 2 structures we drew, that's 1,2-dichloroethane. You see that in the first one, we see chlorine is at the top of the carbon of this first carbon here, and the second carbon, chlorine is under. This is under. Now, that does not make any sense. It's still the same thing as this second structure we are seeing by the right. The reason is you can rotate. If you just check this, use that single bond linking these 2 carbons together. I mean, we're talking about the diagram on your left hand side now. If you hold that as the broomstick now and rotate the other carbon, the right hand carbon, by the time you rotate it, the chlorine that was down will turn and will be staying up. The same way, if you leave this one down like it is, and then you hold the broom and then rotate the chlorine that is up, the carbon, and the chlorine that is up comes down, it will now come down and meet the chlorine that was down here, the other one at the right. Try and understand. You see that it will look like the structure on the right hand side. So we said that it still will remain the same. There is no change. So that's why what is written below reads, the two models represented above are exactly the same. They're the same molecule. They are not isomers. You cannot say they are isomers because there's a free rotation. It can rotate and go back. If you have called it isomer already and then you rotate it, it comes back. You will not say it's not an isomer again. So we don't consider that as an isomer because there is a free rotation. You can draw structural formulas that look different, but if you bear in mind the possibility of this free rotation about single bonds, you should recognize that these two structures represent the same molecule, so we don't consider those isomers. Now, in contrast, that's different, unlike the other one, the double bond in alkenes are rigid, just like you demonstrated. The two broomsticks that created double bond cannot rotate the orange anymore. They are not free to rotate. Example, we have 1,2-dichloroethane. Its restricted rotation about the double bond means that the relative positions of subsequent groups, as in that diagram now, in that structure now, you see chlorine, just like it was the other way, but now it's a double bond. Those are the chlorines, the subsequent groups above or below the double bond becomes significant because you cannot change anytime soon. It's rigid, so it's now significant to you. Now this leads to a special kind of isomerism. So look at that structure. You have chlorine and chlorine all on the same axis, both on the same axis. The structure on the left hand side, chlorine and chlorine both on the same axis, but the one on the right hand side, chlorine is opposite chlorine on the other axis, so it's not on the same axis. So this one on the same axis we said is cis-1,2-dichloroethane, but the other one that is transverse, that is not on the same axis, so trans-1,2-dichloroethane. You will know why the name cis and trans is. The isomer in which the two functional groups, example the chlorine you see there, lie on the same side of the molecule at the same axis, is called the cis isomer. Cis isomer, cis means on the same side, cis on the same side. While the isomer with the two groups, that's the chlorine that is now adjacent, on opposite sides of the molecule is the trans isomer. Trans means across, transverse, transfer, across. Now, this is known as cis-trans isomerism. So if you see, it's just made of cis and trans. Cis-trans isomerism, or in short, we call that geometric isomerism. So what's geometric isomerism? Geometric isomerism is the existence of compounds with the same molecular formula but different arrangements. Same molecular formula but different arrangements, that is, groups permanently in different places in space, due to the presence of a rigid structure in their molecule. Very important. Due to the presence of a rigid structure in their molecule. Now, geometric isomerism is common among alkenes. Remember, alkanes have single bond. They are free to rotate. You cannot consider that isomers because they can rotate. So they are common among alkenes, which have double bonds. Geometric isomers have similar chemical properties but different physical properties. What that means is, you see, those two structures, the cis-1,2-dibromoethane and trans-1,2-dichloroethane, they have the same molecular formula, but because they have changed in structure, the way they are arranged in structure, that's partial arrangements, they will have a slight different chemical property. Now, the trans form of that one to the trans-1,2-dichloroethane, now it boils at 48 degrees Celsius, but the cis form, the cis-1,2-dichloroethane, boils at 60 degrees Celsius. So you see that slight difference in their chemical structure, the chemical properties. Also, the cis form of the 2-butene, of 2-butene, not this one now. If you see 2-butene, cis-2-butene and trans-2-butene, the cis-2-butene will boil at 3.7 degrees Celsius and has a density of 0.641 gram mole, while the trans-2-butene would boil at 0.9 degrees Celsius and has a density of 0.626 gram per mole. So you see the slight difference. That's what you should take note of. Now, we said we have geometric isomerism and optical isomerism under stereoisomerism. We'll discuss geometric isomerism. Now, what is optical isomerism? Optical isomerism is the existence of two or more compounds with the same molecular formula but with different orientation in space due to their effects on plane polarized light. You understand everything, but let me repeat that. Optical isomerism is the existence of two or more compounds with the same molecular formula but different orientation. You almost know that that's generally what isomerism is in space. But now, due to their effect on plane polarized light, the one for geometric isomerism was due to the presence of a rigid structure in their molecule. But now this optical isomerism is due to their effect on plane polarized light. Now let's see what's plane polarized light. Polarized light is light having only a single color. Example, white light. Now, your electric bulb is not one color. You will discover that it's not white light. The light you are seeing there, if it pass through a light spectrum, you see it can disperse so many colors. So, if we have plain, pure white light, that's the example of polarized light. A plain polarized light is light whose electric field oscillates in just one plane. That's because it's just one spectrum that it will create, because it's just a pure color as one spectrum. So optical isomers are two compounds which contain the same number and kinds of atoms and bonds. They contain the same number of atoms and kind of bond, but different spatial arrangements of the atoms having non-superimposable mirror images. Non-superimposable mirror images. Now I want you to do something for me. Carry your two palms like as if you want to do high five. But this high five, you are doing it. You see your two hands. If you carry your two hands, okay, clap your hand. Just put your two hands together as if you want to pray, but don't interfix them. If you put them together, you see that all of them they match, right? But you are turning. Okay, they match very well, right? Good. Now carry that hand apart. Let one stand, and then your face can enter the center. You understand? But the two hands are still open the same way. If you look at that hand like that, you will discover that your right hand side and your left hand side, they are mirror images. The left hand side is just like you will see your right hand side on the mirror. You understand that? If you look at your right hand side on the mirror, it will appear as your left hand side. That's how your left hand side is to the right hand side without the mirror now. They are mirror images. So your left hand side, if the right hand side, the right hand now open now is facing the left, you will see it as a mirror, as if you are seeing your left hand side on a mirror. That's what we call non-superimposable mirror images. Cannot superimpose. Optical isomers must have a carbon atom linked to 4 different groups. If that does not happen, you will not have non-superimposable mirror image. Example, lactic acid and alanine. You see this diagram to draw there. You see the mirror at the center. Now, COOH was at the right hand, but just imagine that you are seeing, this is a plain book, I'm writing that. So imagine that you are seeing it in the mirror. You see that COOH will turn to that as if it's the left hand side, just like your two fingers now, or your two palms now. If you look at them, this from the back of the first hand. Look from the back of the first hand, the other hand is facing the other one. You see the other one acts as a mirror now. So you see that. Just free yourself, do it in a mirror, and you will see what happens. That's what happens to optical isomerism. So now, each non-superimposable mirror image structure is called an enantiomer. Enantiomer. Molecules or ions that exist as optical isomers are called chiral. If you don't like to call it chiral, call it chiral. If you don't like to call it chiral, call it chiral. Anyhow, but just remember to write it in exams. So chiral. Okay. Now let's look at alkanols. Alkanols are compounds in which hydroxyl groups, remember hydroxyl groups is OH, are linked to alkyl groups. Remember what alkyl groups are. Simplest alkyl group is CH3 methyl, and have ethyl, and all those. I would say we can represent alkyl group as R. R can mean so many things, but alkyl can also be represented as R. Remember what we said? I'm just reminding you. They are derived from the corresponding alkanes by replacing the hydrogen atoms with the hydroxyl groups. Now remember, alkanols derive from alkane by just replacing hydrogen. If you replace one hydrogen there, you are going to be adding one OH group. If you replace two hydrogens, you are going to add in two OH groups. So to every one hydrogen you remove from an alkane member, you're going to add one OH group. So if you remove one hydrogen from methane and add one OH group, it now becomes methanol. Alkanol now. It's now an alkanol, not an alkane series now. You should understand that. Now, the hydroxy group is the functional group of the alkanols. That OH is the functional group, as it is responsible for their characteristic chemical properties. Just like as a reminder, remember that we said functional group affects the chemical properties. It affects the whole chemistry of that the family it goes into. Now, most alkanols contain only one hydroxy group in their molecules. Now, when this happens, they are referred to as monohydric alkanols. Monohydric alkanols. Mono means one. Since it just has only one hydroxyl group, monohydric. The monohydric alkanols form a homologous series with the general formula CnH2n plus 1 OH. Because they're just removing only one H. If it was to be an alkane member now, it would be CnH2n plus 2. But now we remove only one H, so it now is plus 1. Then instead of, in place of that one we remove, we now add OH, just like I explained. Since the group CnH2n plus 1 is the alkyl group, remember, if you go back to your table, where we have alkyl, the formula is CnH2n plus 1, which can also be represented by R. Remember that. General formula of the monohydric alkanols can be written as ROH. Remember, R now stands for CnH2n plus 1, then OH joins. So ROH is the same thing as CnH2n plus 1 OH. Just a representation. If you read that, you understand very well. The name of each homolog. The name of each homolog is derived by dropping the end E of the corresponding alkane and replacing it with OL. Remember, if it was methane, just remove E and add OL. You'll be having methanol. So replacing it with OL. The simplest member of the alkanol series is methanol, CH3OH, sometimes known as wood spirit. Now, why is it known as wood spirit? Because it was produced by the destructive distillation of wood in the early days. Take note, methanol is poisonous and can cause blindness if you consume it. So, not that we're saying wood spirit now. You come and carry it and rub in your wound, carry it and sneeze. Alright, it's poisonous. Ethanol, C2H5OH, is a second member of the alkanol series and is the most important. So ethanol is the most important. Methanol is also called wood spirit. I'm giving you highlights that you will see in exams. Methanol is also called wood spirit, and ethanol is the most important member of the alkanol series. As the most important member of the series, it is the essential ingredient in alcoholic drinks. I've told you why. And I told you why the other one is called wood spirit. You cannot blame me anymore. Generally, hydrocarbons are not soluble in water. But see, this one, alkanols are soluble because the hydroxyl groups in their molecule can form hydrogen bondings with the water molecules. Hydroxyl has oxygen and hydrogen. And guess what? Water molecule has oxygen and hydrogen. So they're like friends, they have met. So they have the same kind of bond. They can now interchange. So alkanols can now dissolve in water because of the functional group there. You see how it affects the whole member. Alright. Solubility of alkanols decreases as the number of carbon increases. How soluble, how it can dissolve, how an alkanol can dissolve in water reduces when you increase the number of carbon. Whenever you are doing organic chemistry, consider carbon as the hard substance. So if you are using gari, if you are to sip gari, and then the gari becomes, you soak your gari, and then at the point the water is dry and the gari is strong, it doesn't dissolve, right? What do? You add more water to make it dissolve more, so that you can sip it easily without it scratching your neck. Now, but if you want it to become more hardened, if instead of adding water you're adding more gari, what are you doing? It's becoming less easy to dissolve. That's what it means here. Solubility, that's ability, how soluble, how it can dissolve in water, decreases as the number of carbon increases. Please, you should understand. Now, types of alkanols. There are 3 different types of alkanols. We have primary, secondary, and tertiary alkanols. I'll need your ear. Open your ear, look at that book word to word as I'm going, and look at the diagram as I'm explaining, because this can confuse. A primary alkanol has only one alkyl group attached to the carbon atom that carries the hydroxyl group. What did I say? It has only one alkyl group. When I say alkyl group, think of the smallest one is methyl, ethyl, all those ones, methyl. So it will have only one alkyl group. And what is this one alkyl group attached to? It attached to the carbon atom that carries the OH group. Hydroxyl group is the OH group. So it's attached to the carbon atom that carries the OH group. A secondary alkanol has 2. That's 2 alkyl groups now, but they are still attached to the carbon that carries the OH group. Tertiary alkanol has 3 alkyl groups, but they are still attached to the carbon that carries the OH group. That's what I wanted to take note. Now, see the examples that the number 1, primary alkanol. You see, R is the alkyl group. The alkyl group is attached to C, and this C is linked to OH group. So that means, it's only one R we are saying. We said that R can be used to represent an alkyl group. But look at the example by the right there. You will now see that R, the alkyl there was CH3, HC3, H3C, CH3, the same thing. I just want that C to link to C. You cannot link H to C the way you cannot say H3 then you link it to C. You understand? I want C to be linked to C. That's why I interchange C to be still CH3, still methyl. So that's an example. R is linked to C and that C is linked to OH. So only one R. But you see on the secondary alkanol, it's not 2 R. R and then R prime. The R on top and the R on the left hand side is linked to the carbon that has OH. If you look at the third one, you now have 3 R, then R prime, then R prime prime linked to the OH. So that's tertiary. 3 alkyl groups linked to the OH group, the hydroxyl group, the alcohol group. Now, that's the difference between the primary, secondary, and tertiary alkanols. Some alkanols contain more than one hydroxyl group per molecule. They are known as polyhydric alkanols. Remember we said monohydric alkanols because it contained only one hydroxyl group. But now the one that contains more than one, we call it poly. Poly is more than one. It can be 2, it can be 3, it can be 4. No, but then you can now go ahead to say if it contains 2, you can say it's dihydric. It's 2. But 2 is under poly, it's more than 1. If it's 3, you can say trihydric. 3. But 3 is under poly, so it's because it's more than 1. You can still say tetrahydric, pentahydric, as the case may be. But the case is that the idea there is when it contains more than one hydroxyl group per molecule, then that's a polyhydric alkanol. Now you see that the first one example there, ethan 1,2-diol. Diol means it contains 2 hydroxyl group, 2 alcohol group, 2 OH group. That's what it means. And when we have propane 1,2,3-triol, 3 alcohol or hydroxyl group. Now, what are the rules for naming alkanols? Rules for naming alkanols. Remember the rules we have done those in alkane, alkene, alkyne. Now, alkanols, what are the rules? Alkanols are named by replacing the suffix "n". Remember, it's derived from alkane. So you remove the "n" suffix and replace it with "anol". the same thing as the one I explained there, but the same thing. Can just remove the ANE and add anol. So methane would become methanol. Methanol. Good. Met means 1 carbon atom. Et means 2 carbon atoms. Prop means 3 carbon atoms. But 4 carbon atoms, like that. So that will not change, but the parent, the family name that came in was N, which became methane. So you remove that family name and put this other family name of alkanol. So it becomes methanol, ethanol, propanol, butanol, pentanol. Now, if there is more than one hydroxyl group, the suffix is expanded to include a prefix that indicates the number of hydroxyl groups present, like we have diol, like we did in that just above you, diol, triol, etc. Now, let's see the rules. Number 1, the hydroxyl group takes priority over alkyl groups and other substituents, as well as double bonds in the numbering of the parent chain. Now, when you are naming alkanols, what is OGA is not even the double bond in this case, which is very strange. The OGA, the one you must take note of first, if not you will get angry. One you must take note first is the alcohol group, the OH group. So if this alcohol group in your parent chain, there is double bond in that chain, what do you go for first? What do you give priority to? The OH group. Remember, since the one we have done alkane, alkene, and alkyne, you give priority to double bond. You handle double bond like king. Here, OH group, the alcohol group, is greater than that double bond. So the hydroxyl group takes priority, is the king here. Now, number 2, when both double bonds and hydroxyl groups are present, the en suffix follows the parent chain directly, followed by the position of the hydroxyl group, and then by the ol suffix. You will see that. And the location of the double bond is indicated before the parent name. Now let's look at this example. The first one is 3-methyl-2-pentanol. You see that our first chain did not have double bond, so we don't even have to tell anybody, sorry. It don't have any double bond, it's just a straight chain and 2 groups, subsequent groups there. What are the subsequent groups? The OH group, which is the hydroxyl group, and then we have the CH3 group, which is the methyl group. You should know all these by now. Now, we said OH is OGA, so you have to take note of that one first. So when numbering, you give OH the lowest number. You number the parent chain in a way that OH, the hydroxyl group, will have the lowest number. So you have to number from the left. So you have to number 1, 2, 3 for the way I numbered. So OH group is on the 2nd carbon. Good. Then 3rd carbon is where the CH3 group is. Okay, we've mentioned all the functional group now. Time to write it out. Remember, when you're writing out, you will not give more attention to the OH group now. In writing them out, you arrange them alphabetically. So M has to come before the parent name, which is the functional group is just added to the parent name. So it comes close to the ending. So it becomes 3-methyl because the methyl group is added to the 3. 2-pentanol. The straight chain is pentanol, but where is the all functional group found? On the 2nd carbon. Okay, so it's 2, 2nd carbon, 2-pentanol. And you see the other example, the same thing, 2,3-butanediol, 2,3-butanediol. The 2,3 is where the 2 OH are, 2 and the 3rd carbon, 2nd and the 3rd carbon. If you want to label it from this other way, it will still be 2,3, 2,3-butanediol. And the other one, we have 2-cyclopentane 1-ol. Remember, we did not say pentene 1-ol. It has double bond, so we cannot. It means that it's an alkene there. But see, remember that time we're doing that thing. We said when there is another functional group to mention, you don't say pentene. It's looking like you are ending. You say pentane. You should remember. Then you add the last thing you want to add. So you see that the OH group is on the 1st carbon. That top where I put that OH group, that's the 1st carbon. Start counting to the right. The 2nd point will be the 2nd carbon. The 3rd point will be 3rd carbon. 4th point, 5th carbon. So the OH group is on the 1st carbon. So we know that the how many carbon does the the whole molecule have? If you start from that point, the point that the OH is attached, that's 1, 2, 3, 4, 5. 5. So 5 is pentane, right? Good. But now it has a double bond, so it's pentene. 5 is pentene now. So because that is pentene and OH is in the first carbon, so it will be pentane 1 all. But now we have, where is the ene located? Where is the double bond located? The double bond is located in the second carbon. You should look at that. You understand better when we are physical. So second carbon, so Su2. And remember, we said if the compound you are naming is a cyclic compound, hydrocarbon, then you have to put cyclo to show that it's cyclic, it's not straight. So 2-cyclopentane 1 all. Good. Preparation of alkanols. How do you prepare alkanols in the laboratory or industrially? Number 1, by the hydrolysis of haloalkanes. Should remember, we said that alkanols are derived from alkanes. So you can use haloalkanes. Haloalkanes are alkanes that have halogen functional group in them. And we say halogens are group 7 elements, which include iodine, chlorine, bromine, fluorine, and statine. So now look at this. Haloalkanes, when boiled with an aqueous solution of an alkali hydroxide or moist silver oxide, will produce an alkanol. You see, for that in that example, remember we said X, that halogens are, the functional group is X, where X can be chlorine, bromine, so the R is the alkyl group. So the R is linked with the X function, the halogen there, plus this alkali hydroxide plus potassium hydroxide. Now when that happened, we formed an alkyl linked with an alcohol group, ROH. Remember when we said that's the formula, it can be the formula ROH plus KX. You see that? And the second way, the same thing. But look at that third one. C2H5Br is a haloalkane. C2H5 was supposed to be C2H6, but bromine came in to replace one of the H, so it became C2H5Br. So it's an haloalkane. Bromine is an halogen. So halogen attached to an alkane, haloalkane, plus silver hydroxide, which is an aqueous solution of alkali hydroxide. It's an alkali hydroxide. So that was combined together, and what did we have? C2H5OH. OH just changed name, but remember, when you do SS2, you understand. For SS1 students, for SS2 students, you understand what I mean. Hydroxide changed neighbor, and then for C2H5OH was formed. C2H5OH is now an alkanol. Which alkanol is that? Ethanol. So that's the first way, hydrolysis of haloalkanes. Number 2, we have by hydration of alkenes. Hydration means adding hydrogen. How do you add hydrogen? By adding water. Water has hydrogen in it. If you see that formula, you will understand very well the structure, how it's done. By fermentation of carbohydrates. Now I want you to look at that. Here, sucrose is first converted to glucose and then fructose with an enzyme. That enzyme is what? Invertase. Invertase. The fermentation process is carried out under anaerobic condition. Anaerobic condition is absence of air. Carbon 4 oxide released during fermentation keeps the mixture out of contact with air. Now, if the fermentation mixture is exposed to air, you see that the oxygen in the air oxidizes ethanol to ethanoic acid, which makes the mixture too sour. So that's what happened when the people producing fufu, when they ferment cassava, ferment that, this is what happens. Now, ethanol is obtained from starchy mixed materials such as barley, millet, rice, maize, cassava, unripe banana, and potatoes with enzymes. These enzymes can be diastase and maltase. Go and drink malt. Okay. Now, look at that structure. That structure I wrote. We said first of all, you see that starch. it has to be broken down to maltose. Then maltose has to be broken down to glucose. Then glucose now broken down to an alcohol. That's why you see when they are fermenting cassava, they keep it for days because this process has to take place. All this has to take place. When it ferments, you see it tastes sour. It can high you. Don't take them direct like that. So, all right. So now look at the structure. Starch. Starch was fermented using an enzyme, diastase, to break it down to maltose. Now, maltose, which is a product now, was now taken to the process again using maltose itself as an enzyme. It was broken down to glucose. Glucose is just sugar. When it became glucose, glucose had to pass through another process also and was broken down using zymase as the enzyme, and then you formed an ethyl alcohol and then ethanol. So that's how to produce an alcohol, an alkanol, by fermentation of carbohydrate. It's very important. You see that those three structures, from starch to maltose to glucose, those three they are very important. In WAEC it comes. Fermentation of carbohydrate yields ethanol containing water. And further concentration is done by fractional distillation. Now, see, this produces a solution containing 95% ethanol. Remember, 95% ethanol. This 95% ethanol is called rectified spirits. Rectified spirits. Take note of all these things are underlined. Rectified spirits. So 95% ethanol produced from the fermentation of carbohydrates is called rectified spirit. Further purification of rectified spirit, how do you purify it? By distilling over quicklime, results in absolute ethanol. Absolute ethanol. That's very pure. Now it contains 99.5% ethanol. So just little impurity. But the other one had 5% impurity. So rectified spirit is not as pure as absolute ethanol. Alright. Now you see combustion of alkanols. How does alkanol burn? Alkanols are flammable. Why are they flammable? Because they have carbon atoms in them. So they burn in air because of the presence of the hydrocarbon chain in their molecule. They burn to produce carbon dioxide and water, just like every other hydrocarbon. So you know what formula you can use for the conversion? You remember. Now, this is what happens. Methanol, you will see when methanol burns in air, it will produce 2 moles of carbon dioxide and 4 moles of water. So when ethanol burns, it produces 4 carbon dioxide and 6 water. You see how that thing is going. Then propanol, 6 carbon dioxide and 8 molecules of water, and it goes that way. Have you seen that? Ethanol has more carbon, so it produces more carbon dioxide and more water. Propanol has more carbon than ethanol, so it produces more carbon dioxide and more water. Butanol has more carbon and hydrogen than even propanol, so it produces more carbon dioxide and more water molecules when it burns in air. So that's the combustion of alkanols burn. Now, esterification. Alkanols react reversibly. When you say reversible reaction, it means it can return to the former state. It's a reversible reaction. And reversible reactions, you use that arrow, the 2 arrows facing both ends. It means a reversible reaction. Alkanols react reversibly with acids forming ethyl esters. This process is known as esterification. Now, this thing is leading us somewhere. Esterification is in SS3. So for the SS2 student, it's telling you that you're ready for SS3. Alright, so you see the example. Alkanol plus acid produces in a reversible reaction ester plus water. It means if you see it produces ester plus water. Why is it reversible? How can we reverse it? If you remove water, ester forms back to alkanol and the acid. You understand that? Because the other one it was plus water. So if you add hydrogen, or if you remove hydrogen, that's you're removing water. You understand that? That's an example there. Ethanoic acid plus ethanol will produce in a reversible reaction ethyl ethanoate, which is an ester, plus water. Remove the water from it, it will go back to what it was. Now, what are the uses of alkanols? Remember when we said the other way, methanol is used in making methylated spirit. We said methanol is called a wood spirit, so it's used in making methylated spirit. Number 2, ethanol is used as alcohol in alcoholic beverages such as beers, wines, and spirits. Example of spirits are whiskey, dry gin, brandy, rum, etc. So that's why ethanol is most important in that family. Family of drunk. Let me not even say anything. Number 3, ethanol is used to dissolve resins. Resins are like glues, gum, the strong gum, strong. If you are doing carpentry, if you go to carpenter workshop, there are strong gums they can apply to wood. You may not even need nail again. Resins. Ethanol is used to dissolve resins. Varnishes are those things that make your table smooth, your wooden table smooth. They will apply it and it becomes glossy, looks like mirror. Those are varnishes. Likewise, also like varnish. Then soap, perfumes, dyes, drugs, and flavoring agents. So ethanol is dissolving agent. Can be used to dissolve so many things. Now, due to its low freezing point, that's minus 17 degrees Celsius. Now we're talking about ethanol too. Ethanol is used as antifreeze in automobile radiators in cold countries to prevent those things from freezing. So use ethanol. Ethanol is used to sterilize wounds and syringes. If you look at movies, you want to do hard men, gunshot. Somebody shot with gun. You see, he removes one dry gin from his pocket, drinks it, and then pours it on the wound. Just trying to sterilize the wound. Sterilize means to remove bacteria, and you sterilize everything that was going to attack that wound is killed, and that the harshness of what you are pouring on it. So ethanol can be used there. That's why it's in dry gin. Ethanol can be mixed with petrol, up to 25%. Though you don't go and carry dry gin and pour inside petrol tank and start driving. Can be mixed up to 25% and used as fuel in internal combustion engine. So it's not everything you mix there. So at this point, you've seen a lot about hydrocarbons and organic chemistry. I know you may have questions. When we resume physically, we will have enough time to deal with these. But if you have immediate questions you want answered, drop it on the group and I will answer them. Make sure you do your assignments also. All right. Have a nice day.